All right, so you know how much we're always talking about the potential for self-driving cars, right? Well, getting these vehicles actually road ready, well, that's a huge undertaking. And a big part of it is making sure they're trained for basically like every possible situation.
Yeah, totally. And a lot of this training happens in simulations, but these simulations, they often rely heavily on data sets that come from real-world driving.
Yeah, it's kind of like, trying to learn how to dance, but you're only ever watching like one person dance.
Right. You might get really good at like their style, but then what happens when you need to adapt to a different, song or a faster beat?
Right, exactly. So today we're going to deep dive into a paper that proposes a really novel approach to generating diverse and realistic scenarios. Like, think of it as building a variety of dance floors for these autonomous vehicles.
Yeah, and I think that's such a great way to put it. The limitations of relying solely on like a single real-world data set, that really becomes a bottleneck when you're trying to train for those less common or unexpected situations.
It is. And the researchers in this paper really highlight this idea of corner cases, right? Those really tricky situations that can really kind of expose the weaknesses in a driving algorithm.
Absolutely. And I think this is a critical point.
Yeah.
Because if you think about it, like a car might be fantastic at navigating, your typical suburban street on a sunny day. But what if it encounters a flash flood or a really unexpected detour?
Yeah, something that it's never seen before, right?
Exactly. And that's when things can get a bit unpredictable and potentially even dangerous. So the researchers here, they introduce a framework called DriveGen.
DriveGen.
And DriveGen uses LLMs and VLMs. Those are large language models and visual language models.
And these are the models that are driving a lot of those, advancements we keep hearing about in AI and language and image understanding.
Exactly.
Okay.
And so they're using these advanced AI models to actually create those diverse scenarios that we've been talking about. And not just any scenarios, but specifically those corner cases, those really challenging ones that we want to stress test the driving algorithms with.
And they even went a step further, right, and developed an extension of DriveGen. They called it DriveGen CS.
Yeah, DriveGen CS. And that focuses on automatically generating those corner cases.
So for our listeners out there who are really into the future of self-driving cars, what's the key takeaway? What's exciting about DriveGen?
So for me, the really exciting thing about DriveGen is that it's a two-stage framework, and it leverages the power of those LLMs and VLMs to generate this much broader and more realistic spectrum of traffic scenarios.
So it's almost like an AI that can not only understand the rules of the road, but also dream up entirely new road layouts and the complex interactions that could happen on them.
That's a great way to put it.
So let's dive into the details a little bit. How does DriveGen actually work?
Okay, so the process starts with what they call scenario initialization. And this is basically setting the stage, like creating the virtual environment for a self-driving car.
For building the virtual world.
Exactly. They use a large language model. The paper specifically mentions Claude Three-Ocus.
Claude Three-Ocus.
And it's a very powerful LLM for understanding and generating text. Now, they combine that LLM with something called a retrieval technique.
A retrieval technique.
Yeah, and this technique uses both rule-based knowledge about, how road networks are designed and examples of different kinds of road situations.
So intersections, roundabouts, highways.
Exactly, all of that. And so using all of this information, the LLM can actually generate what's called a SUMO network definition XML file.
SUMO.
Yeah, it stands for Simulation of Urban Mobility.
Okay.
And it's basically like a digital blueprint for the road network.
So it's defining the roads and intersections and all of that.
Exactly. And what's really neat here is that you can even give the LLM just a text description, like a busy intersection with a dedicated left turn lane and tons of pedestrian traffic. And it can actually generate a digital roadmap that matches that description.
So it's you're not just limited to recreating traffic situations from existing data sets.
Right. DriveGen can invent these entirely new virtual worlds for autonomous vehicles to learn in.
Okay, so that takes care of building the roads and the environment. What about the cars themselves?
So yeah, the second part of this initialization stage is called vehicle assets generation. And what they've done here is they've created a database of different types of vehicles. And this database is informed by real world data, the kinds of vehicles you actually see on the road.
Gotcha.
And then when they're creating a scenario, the system decides how many cars are going to be in it, what types they are, and then it pulls those digital models from this database.
Okay, so if they decide they want a semi-truck in the scenario, it pulls that 3D model into the virtual world.
Exactly. and they designate one of these vehicles as the target vehicle.
So that's our self-driving car, the one being tested.
Yeah, and all the other vehicles are called social vehicles.
Social vehicles, okay.
And they place all these vehicles on the map that was just generated, giving them realistic starting positions and speeds and things like that. All those details that set the scene for some good traffic interactions.
So we've built our virtual world, we've populated it with cars. Now, how do we get these cars actually moving and interacting in a realistic way?
So that's where the second stage comes in, and that's called scenario rollout. And this is about bringing the virtual world to life, like making the traffic flow and making it dynamic.
So the cars actually start driving around.
Exactly. And they use information from the simulation environment, like image data of what the vehicle would see through its virtual sensors.
Like its cameras and LiDAR and all that.
Yep. And they feed this information to a visual language model. In this paper, they use GPT-4 Turbo.
GPT-4. So they're using GPT-4 to make driving decisions. That sounds incredibly advanced.
Yeah, it's super cool. But they don't just ask GPT-4 to directly output like all the tiny movements of the car, because that can get super complex.
So how do they use it?
They take a more structured approach.
Yeah.
First, they use a rule-based system to identify all the possible routes and destinations or like intermediate goals that a vehicle might have.
So like figuring out where each car could plausibly go.
Right. And they represent those goals as these little waypoints in a bird's eye view image centered on the vehicle.
So it's like giving the VLM a set of possible destinations for each car.
Exactly. And they feed this image along with the text description of the current traffic situation to the VLM.
So the VLM can see both like a map of where the cars are and some text describing the traffic.
Exactly. And then the VLM analyzes all of that information and it ranks the possible goals based on how likely they are for a vehicle in that particular situation.
Okay, so the VLM is making like high-level decisions about where the surrounding traffic might go next.
Yeah, like it's thinking about what makes sense in the context of the current traffic flow.
Got it. But we still need to turn those high-level decisions into smooth, realistic driving movements, right?
Absolutely. And that's where their diffusion-based trajectory planner comes in.
Diffusion-based?
Yeah, it's based on these cool AI models called diffusion models.
Okay.
And they've trained this really sophisticated neural network to generate realistic driving trajectories, the actual paths that the cars follow. And it does this by modeling a process of like gradually adding noise to real-world driving data and then learning to reverse that process.
So it's learned to kind of undo the randomness and generate smooth paths.
Exactly. And they feed it the initial state of the vehicle and the goal waypoint that was chosen by the VLM, and it outputs a nice smooth trajectory for the car to follow.
And it also uses the road map information, right, to make sure the car stays on the road.
Right. It incorporates all of that information.
Mm-hmm.
And then as a final step, they have what they call a legal checker.
A legal checker.
Yeah, it's like a safety net. It makes sure that all the generated trajectories, like the paths the cars are taking, that they follow traffic rules, that they don't cause collisions, and that they stay within, the physical limitations of the vehicles.
So it's making sure everything is safe and realistic.
Exactly.
Yeah.
And if a trajectory fails those checks, it gets regenerated until they find one that works.
So it's like the system is really trying hard to generate scenarios that are not just diverse, but also believable. But you mentioned earlier that this paper also talks about generating those tricky corner cases.
Yes. The really challenging situations that are designed to kind of trip up the self-driving car and see how it handles them.
And you mentioned DriveGen CS for that. So how does that work?
So DriveGen CS builds directly on the foundation of DriveGen. It uses all the same basic mechanisms. But the key difference is that it uses information about where a particular driving algorithm has failed in the past.
So instead of just generating random scenarios and hoping they'll be challenging, it's like specifically targeting the weaknesses of the driving algorithm.
Exactly. And they do this by taking data from collision scenarios. Instances where the self-driving car actually crashed in a drive-generated scenario.
Okay.
And they analyze those collisions in detail, extracting information about the moment of impact.
So things like the speeds of the cars involved, their headings, what the self-driving car was doing just before the crash.
All of that, yeah. And by examining lots of these failure cases, they can statistically identify which combinations of those factors are most likely to lead to a crash for that particular driving algorithm.
It's like building a fingerprint of the algorithm's weaknesses.
That's a great way to put it. And they use this failure fingerprint along with visual images of the collision scenarios to guide the VLM when it's choosing goals for the social vehicles.
So it's like saying to the VLM, hey, I know this driving algorithm struggles with situations like this, so try to create a scenario that will test that weakness.
Exactly. So the system isn't just randomly generating dangerous situations, it's intelligently designing scenarios that are tailored to really challenge the self-driving car.
That's really cool. And you mentioned earlier that this approach is a lot more efficient than some of the traditional methods for generating corner cases.
Yeah, definitely. In the past, generating those really tricky corner cases often involved a lot of manual effort from engineers.
So people would basically have to hand design these scenarios.
Right. Or you would have to retrain the whole scenario generation system every time you made even a small change to the driving algorithm.
And that could take a lot of time and computing power.
Exactly. But DriveGen CS sidesteps all of that by directly using the failure information as input for the VLM.
So no need to manually design scenarios or retrain the whole system.
Right. And the researchers show that this approach is not only more efficient, but it can also generate corner cases that are much more effective at finding those vulnerabilities in the driving algorithm.
So it's a win-win, both more efficient and more effective. Now, I'm curious, to put this work in context, what's been the historical trajectory of research in machine learning for autonomous driving that's led to DriveGen?
Yeah, that's a great question. So early on, when machine learning was first starting to be used for autonomous driving, there was a lot of focus on imitation learning.
Where the AI is essentially trying to copy what human drivers do.
Exactly. And, that got us pretty far. But as we started aiming for more complex behaviors and we really wanted to make sure these cars were robust in all kinds of situations, we needed to move beyond just imitation.
And that's where reinforcement learning came in.
Right, reinforcement learning, where the AI learns through trial and error in a simulated environment.
So it's like the AI is getting virtual rewards for good driving and penalties for mistakes, and it learns to maximize the rewards over time.
Exactly. But the thing about both imitation learning and reinforcement learning is that they're really dependent on the quality and diversity of the data that you train them on.
So if you only train them on sunny day driving in suburban neighborhoods, they might not do so well in a blizzard on a mountain road.
Precisely. And so creating these diverse and challenging simulation environments has always been a big bottleneck.
And how did we try to overcome that bottleneck in the past?
So early simulation tools often relied on very simple rule-based models for the other cars in the environment.
So the other cars weren't really intelligent. They were just following a pre-programmed set of rules.
Right, and that made them pretty predictable, not very realistic compared to how human drivers actually behave.
And so we started exploring more sophisticated ways to generate traffic, like using generative models.
Exactly. But those generative models, they were often limited by the data they were trained on.
Yeah.
The real-world driving data that we had available.
So it was like we were still kind of stuck in that loop of only being able to generate scenarios that we had already seen in the real world.
Yeah. And then came the big boom in large language models and visual language models, the ones that can understand both language and images.
And that's where DriveGen fits in.
Exactly. These models, they bring a whole new level of understanding and reasoning to the table. They can understand complex situations in a way that just wasn't possible before.
So we can finally move beyond just replaying recorded driving data and start generating these truly novel and interesting scenarios.
That's the key, and that's why I think DriveGen is such a significant step forward in this field.
Okay, so to recap for our listeners, what are the key contributions of DriveGen?
So first and foremost, it tackles that problem of data diversity, which is crucial for training and testing self-driving cars.
And that's something that's been a major roadblock for a long time.
It has. And then DriveGen has this clever two-stage architecture that combines LLMs for high-level scenario design and VLMs and diffusion models for generating those realistic driving behaviors.
So it's bringing together the best of both worlds, the language understanding of LLMs and the visual understanding of VLMs.
Exactly. And another key point is that it includes this capability to generate the roadmap itself, which gives us a ton of flexibility in creating diverse training environments.
So we're not limited to just existing road networks anymore. We can create entire virtual cities if we want.
Exactly. And then there's DriveGen CS, which gives us a much more efficient and targeted way to generate those challenging corner cases without all that manual work or retraining.
So we can really zero in on the weaknesses of a specific driving algorithm and test it in the most challenging situations possible.
Exactly. And the researchers showed that these scenarios, the ones generated by DriveGen, they're actually better at training and evaluating autonomous vehicles than some of the best existing methods.
So all in all, it seems like DriveGen has the potential to really advance the field of autonomous driving. What kind of real-world impacts might we see if this technology becomes widely adopted?
So I think the potential impacts are really exciting. Firstly, technologies like DriveGen could significantly speed up the development of self-driving cars.
Because we wouldn't have to spend as much time and money collecting all that real-world driving data.
Right. And that could mean we see self-driving cars on the road sooner. And because we can test these vehicles in a much wider range of scenarios, including those really challenging ones, we could also see improvements in safety.
So potentially fewer accidents and safer roads for everyone.
Exactly. And then there's the potential for more targeted development using DriveGen CS to specifically address the weaknesses of different driving algorithms.
So it's like giving each self-driving car a personalized training program based on its strengths and weaknesses.
Exactly. And I think all of this points to a future where self-driving cars are more reliable and more trustworthy.
And that's something we can all get behind. All right, so now it's time for our Novel Notions segment, where we take the ideas in the paper a step further and imagine what the future might hold.
Okay, I like this part.
So based on DriveGen, what are some exciting research directions that could push the boundaries even further?
So one direction that I think is really interesting is exploring how we can build in even more sophisticated causal reasoning into the VLM.
So right now, the VLM is mainly focused on predicting what will happen next based on the current situation.
Right, but what if we could give it the ability to reason about cause and effect in a deeper way?
So like, if this happens, then that might happen as a result.
Exactly. Like imagine if we could prompt the VLM to think about hypothetical scenarios like, what if a social vehicle suddenly gets a flat tire?
And how would that affect the flow of traffic?
Right. And we could even go a step further and say, okay, how would a cautious AI driver react to that situation versus an aggressive AI driver?
And then we could see how that difference in driving style might lead to different outcomes.
Exactly. And I think this would allow us to generate even more novel and insightful edge cases, those really unusual situations that we might not even encounter in real-world data.
So it's like running virtual thought experiments to see how different AI drivers might respond to all kinds of unexpected events.
That's a great way to put it.
Yeah.
And that could help us uncover potential safety risks that we hadn't even thought of before.
And maybe even lead to new insights into how we can design AI drivers to be even safer and more reliable.
Absolutely.
So that's one exciting direction. What's another one?
Another really interesting possibility would be to create a more tightly integrated system where we take the failures that DriveGen CS identifies and feed them back to the LLM that's used in the initial scenario generation phase.
So instead of just using those failures to generate more challenging scenarios, we actually use them to improve the way the scenarios are generated in the first place.
Exactly. So imagine if the LLM could learn from those failures and start to proactively generate scenarios that are more likely to lead to interesting and challenging situations.
So it's like the system is constantly learning and getting better at finding those edge cases.
Right. And this could lead to a kind of self-improving simulation environment where we're constantly pushing the boundaries of what we can test.
That's fascinating. It's almost like we're creating a virtual world that's specifically designed to challenge and improve our self-driving algorithms.
And that could have a huge impact on the speed and efficiency of developing truly robust and reliable autonomous vehicles.
Absolutely. It really highlights how these advancements in AI, particularly large language models and visual language models, are opening up so many new possibilities in the field of autonomous driving.
For sure. And it's really exciting to see where this research goes next.
Definitely. And for our listeners who want to dive deeper into the technical details of DriveGen, we'll have a link to the paper in the show notes.
Right.
But before we wrap up, it's worth pondering, as these AI models keep getting more and more advanced, what other aspects of the autonomous driving development process might they revolutionize?
Yeah, it's exciting to think about.
I mean, could we see them being used to simulate sensor data? Like what the car's cameras and LiDAR see even more realistically?
Yeah, for sure.
Or could we use them to design more intuitive and user-friendly interfaces for interacting with self-driving cars?
Totally. I think there's a lot of potential there.
And maybe even they could help us redefine what we consider to be a truly comprehensive and effective driving scenario for testing and validation.
Yeah, I think that's a really profound thought. Like, as our understanding of AI and driving evolves, what will we consider to be the gold standard for testing self-driving cars?
Lots of exciting questions to explore as we move forward in this field. Thanks for joining us for this deep dive into DriveGen.
It's a pleasure.
Until next time.